Hello, welcome back. This is part 2 of this trigonometric example that we're doing. We're solving a trigonometry problem using sacred geometry, and in the previous video I created what you see in front of you, and then in between that video and this video I just shaded it in so it looked a little bit more artistic, and that's the only thing I changed between these two videos. I just added some color to show you that, sacred geometry is beautiful. Okay, in order to move forward, you have to know that the internal angles of a triangle, of a right triangle, add up to 180 degrees. If this is 57 degrees and this is 90 degrees, 180 minus 57 minus 90 gives us this angle right here, which is 33 degrees. Okay, now we're going to draw that right on this image. This is 33 degrees. So we have 33, 57, and 90. Those add up to 180. Okay, now here is the kind of flash of genius that you need to have. I mean, everybody can have it, so just follow along. We know that this distance, from my finger here to my finger right there, those points, this distance is the cosine for 57 degrees. Is it clear? I hope, because this is a unit circle of radius 1. This is 1. This is 1. That if this is the cosine of 57, then if I were to turn this whole thing on its side, and we now think of this as my vertical axis and this is my horizontal axis, I'm now kind of looking at the 33-degree angle. If I'm thinking about sine as the y-axis or the height, the sine of 33 degrees, pay attention, is this, same length. So we could say the sine of 33 degrees is equal to the cosine of 57 degrees. Now, that's a right angle triangle property, and it's crucial to moving forward with the solution to our problem. Now, if you have done this problem in class, you are told to think about opposite, adjacent, and then you have to use a trigonometric function called the tangent. Now, the tangent can be drawn in this image, and I will show it in a different video. But let's just assume that we live in a universe where we don't know about tangent. We only know that sine is the height, okay, in this example, and that cosine is the horizontal distance. Okay, the length from me to the wall is right here, or the length from you to the wall is right here. The height of the point formed by a 57-degree angle to the wall is at this point where my right finger is pointing now. So this distance right here is the sine of 57 degrees, or the height of the angle formed by 57 degrees to the ground. That's the height. I can also observe that right triangles can be flipped and turned and twisted, okay, and that since the internal angles must add up to 180, this angle over here is 33 degrees, and that the sine, let's only talk in terms of sine, the sine of 33 is that same distance. So it doesn't matter how I look at it. If I say sine of 33, I'm talking about this distance here. If I say sine of 57, I'm talking about this larger distance here. If I say cosine of 57, I'm back to talking about this distance. So sine of 33 is equal to cosine of 57. That is the relationship that we are about to exploit or utilize in order to solve our missing piece, that height right there. We're going to solve for that. Now, let me walk through this in a mechanical fashion. We need the radian measurement in order to continue, and that's all we need. If we know that we're working with a unit circle, and guys, remember, we're not yet back to the initial problem. We're working here with a unit circle. This radius is 1. See, I labeled it 1. The radian measurement of 57 degrees, this piece of the circumference made by this arc, was right there. That's the radian measurement of 57 degrees. I did 57 times 2 over 360 times pi and came up with 57 pi over 180. And then I multiplied out the number pi using my approximation, my decimal approximation, and I came up with this number. That is for a unit circle of radius 1, that is the radian measurement of the portion of the circumference inscribed by the arc of 57 degrees. This distance. Take a piece of string, make that little bit of string. That's what this distance equals. If the total circumference of the circle is 2 pi r and r is 1, that's the total circumference of the circle. This is the portion of the circumference inscribed by 57 degrees. That's the radian measurement. So, in order to proceed, I need to find the radian measurement for 33 degrees. Because now I'm thinking about this. I'm thinking about it like that. So I need the radian measurement for 33 degrees. Well, let's think about that. We can do it in our heads. The formula for the radian is just degree times 2 over 360 times pi. So if I take 33 times 2, I get 66 over 360 times pi. Now, so imagine in your head, I'm not going to write it, I want you to think about it. Imagine 66 over 360 times pi. Can you reduce the fraction 66 over 360? You can. You can do 33 pi over 180. Because I can divide out 2. I can divide 2 out of 66 to get 33. And I can divide 2 out of 180, 2 out of 360 to get 180. Okay? So this is a reduced fraction, 33 pi over 180. (33 pi of 180 is the radian measurement of 33 degrees. If I were to redraw this whole circle and I measured the radian measurement of 33 degrees, it would be 33 times pi divided by 180 for a unit circle of radius 1. So I'm going to take a new piece of paper and I'm going to transform this triangle. I'm going to flip it and turn it so that we can find this right here is what we need to find, this distance. Now I know what you're thinking. You said, well, we need to find this distance. But I'm saying, look, we're only going to work with sine. So I can't say cosine because I have no idea how to find that algebraically. Remember, my goal here is to not use a trig function in a calculator. So I've got a little trick up my sleeve to find the sine using only radians and the degree measurement. this little trick that I'm about to show you. So I need this distance. I need this distance. Okay? So, let's proceed. I'm going to put a new piece of paper down. And I'm actually going to, rather than redraw the whole thing, I'm going to use a cheater method. I'm just going to create a triangle on a piece of paper. So I'm going to draw kind of a construction line right here. And then I'm going to use my cheater tool rather than the sacred geometry for now, because I'm trying to maximize the efficiency of your time. And I'm going to swing this little cheater arm down here to 33 degrees. So first I better find 33 degrees on this thing. So that's 30, 31, 32, 33. There we go. So swing this back. Right there. Right there. So I'm going to make a couple of marks so that I can get my angle correct. And now I'm going to connect these dots. All right. Now, how do I make that final line? Go over here and be very careful. That's how you do it. Put this on 90 and wait till you see that point pass through it. There we go. So make sure it's straight. Okay. So I'm about to have my triangle set. Okay. For the purposes of this visual, as a visual aid, this will suffice. Let me just darken the lines in and then continue. There's no rush here. So people are very impatient to get to the answer. And the whole point, guys, is the journey. It's not the destination. Okay. We can erase this construction line. That's why it's important to make it nice and soft so it can be erased. And all you're left with is the triangle, which is an approximation. We didn't use sacred geometry to find it, but it's close enough for government work. So here's what we know. We know this is a right angle. And we know that this is 33 degrees. So if this is 33 and this is 90, this over here is 57 degrees. Before we move on, I want to make sure that you understand what I've just done, why I'm doing it. Let me compare these side by side. All I did was move the triangle around. I moved the triangle around. It's the same triangle. Okay, I just moved it around. That's all I did. So now, let me complete. Remember, this is going to represent radius 1. So let me just complete a quick circle around this so we establish what we're doing. In order to create that vertical line, I need this point here. I need to mark that point. I need to kind of hop around this circle a bit. Okay, so I'm never going to find it. Perfect. That's great. All right, so I'll just use my protractor one more time. We'll find the 90-degree angle for the point that passes right through the center there so we can get going. Okay. Now I'm going to draw this in, put my point right there, and draw this in here. There's my 90-degree line. Okay. And just like the other triangle, this is still radius 1. All right. So if I'm doing the radian calculation, remember we said it was 33 pi over 180. I'm going to use my other compass that's got the pen in it and place the pointy end at the origin. And just darken this part of the circle in. Okay. So this distance from right here to right here is equal to the radian of 33 degrees, which was 33 pi over 180. Radians. All right. The whole circle was 2 pi radians, so this is 33 pi over 180 radians for a unit circle of radius 1. This is the key. All right. So now we're going to introduce something called the Taylor series. But before I do that, let me just point out the sine of 33 degrees is represented by this height. You see that? The sine of 33 degrees is this distance. if I show this circle again, the sine of 57 was this longer distance here, but I showed that 57, 90, 33, that this distance right here is the sine of 33, and then I just redrew the triangle so that it was oriented to the page in a way that made more sense visually. Since we're used to reading sines as the vertical distance, you don't really need to. We could have read the sine right off that page there, but this makes more visual sense, and I didn't change anything about the problem. So we're looking for this distance right here. And the reason I need to get everything in terms of sine is because this thing that I just said introduced called the Taylor series, it uses the sine to approximate to a number of decimal places that is truly extraordinary. Many, many decimal places it uses the sine to approximate that, and it incorporates the sine and the radian measurement of the angle. So the way we say it is the sine of 33 degrees is equal, and now we're going to be using radians, to 33 pi over 180 let me get I need to keep my line straight here. 33 pi over 180 minus, and then this is where it gets a little bit complicated, so pay attention closely. 33 pi over 180 to the third to the power of 3 divided by 3 factorial. I'll explain. And it's represented by 3 factorial is 3 exclamation point. Plus (33) pi over 180 raised to the fifth power divided by 5 factorial. Again, I will explain what that means. It's not hard. It's actually very interesting that that's the case. And then at the end we subtract out 33 pi over 180 raised to the power of 7, all divided by 7 factorial. And the reason that this is the equation for the sine of 33 degrees is because the Taylor series that we're using, this is the Taylor series, okay, is because the sine of x is equal to x in radians minus x3 over 3 factorial. This is the general form, so you can do this with any angle to find the sine of any angle. Remember, this is in radians though. So the sine of the angle in radians. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. So that's the general form of the Taylor series. I'm going to mark that off so it doesn't become confusing. The Taylor series for sine. That's what that is. I'm actually going to write that in here. This is the Taylor series for sine of x. So let's work it out. Let's work it out. Now this is where I'm going to rely on Google, because what I promised you in the beginning of this was that we would approximate the numbers we were looking for without referring to any trigonometry tables. So this is what I was getting at, is that I was going to use a decimal approximation. So we used the Taylor series to get a decimal approximation, but as you'll see, we come up with some enormous numbers, or at least some numbers with lots and lots of decimal places. And while I am perfectly capable of multiplying 33 times pi over 180 and then multiplying itself by, over and over and over again to get the power of 3 and then divide by 3 factorial and go on and on and on, it's easier just to put the whole thing into Google, because Google can function like a big calculator, and I'll show what I'm doing. All right, but before I do that, I need to explain what factorial means, because this may be the first time you're hearing that word. So go over here, and there's a little quick mini tutorial on factorials. Factorials are easy and fascinating. Okay, here's how it works. 3 factorial equals 3 times 2 times 1. That's it. It's not any harder than that. So 3 times 2 is 6, times 2 is 6, pardon me, 3 times 2 is 6, times 1 is 6. So 3 factorial equals 6. 5 factorial equals 5 times 4 times 3 times 2 times 1. So let's do it in our heads. 5 times 4 is 20. 5 times 4 is 20 times 3. 20 times 3 is 60. Pardon me. That's right. 20 times 3 is 60. 60 times 2 is 120. 120 times 1 is 120. So 20, 5 times 4, 20, times 3 is 60, times 2 is 120, times 1 is 120. Let's do 7 factorial. This might actually get pretty large. You see this grows very, very fast. So that would just be 7 times 6 times 5 times 4 times 3 times 2 times 1. I don't know if we'll be able to do that in our heads, but we can certainly try. No, I'm going to run out of steam pretty quick. So let's just do it on the calculator. 7 times 6 times 5 times 4 times 3 times 2 times 1. 5,040. So 3 factorial is 6, 5 factorial is 120, 7 factorial is 5,040. So those are the denominators. Actually, I was going to use Google, but I'm not going to use Google. I want to do it right here on this piece of paper, just to show you that it's possible with a 4-function calculator and a little bit of patience to accomplish great things. Let's do it, just for the sake of doing it. So first I need to find what 33 pi over 180 equals, because that gets used a lot. 33 times 3.1417 divided by 180 equals 0.575978. We'll just carry it out to four or five digits, and I'll just put over here sidebar. Do this over here. I'll write this so I don't forget. 33 pi over 180 equals 0.5759. Will round up to 8. That's the radian measurement. That's this distance here. I hope that's clear now. Okay, so we're going to do this crazy arithmetic. Got to just be careful that we don't write it down incorrectly. Okay, so we're approximating the sine, which is this height right here. We're going to use the Taylor series right here for sine, and we're going to compute it out. So let me do some intermediate steps here. This equals, referring back to our decimal approximation of the radian, 0.57598 minus, and here we go, 0.57598 cubed over 3 factorial, which we computed out to be 6. So that's 0.57598 cubed over 6 plus 0.57598 raised to the 5th. And then that's going to be over 5 factorial, which we computed out to 120. Then minus 0.57598 598 raised to the 7th divided by 7 factorial, which we calculated out to be 5040. 5040. Okay, so now we're gonna compute each term. So equals sign 0.57598 minus. All right, here we go with the calculator. You follow along with your calculator. 0.57598. Now this one wants us to cube that number. So times 0.57598 times 0.57598 equals, well, 0.191083. Okay, you see that? But then we divide that number, we divide that by 6. So divided by 6 equals 0.0318. So this is 0.031847. All right, plus. Now we're going to do 0.57598 raised to the 5th. So let's just keep that in mind. So now we're going to do times 0.57598. That was 2. 0.57598. That was 3. 0.57598. That was 4. 0.57598. That's 5. So 0.063392. But remember, we divide that by 120. Divided by 120 gives us this very small decimal here. 0.0000528. All right, minus. See, these are small numbers. Okay, here we go. 0.57598. Now we're going all the way to the power of 7, so we got to be careful. I'm going to call it out. Times 0.57598. That was 2. 0.57598. That was 3. 0.57598. That was 4. 0.57598. That was 5. 0.57598. That was 6. 0.57598. That was 7. So 0.02103. Remember, we divide that by 5040. Divided by 5040. Gives me this very small number here. Point, and then there's 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros, and then 417273. 417273. I know I wasn't consistent with the significant digits, but these numbers are so small it doesn't matter very much. So now all we need to do is a simple addition and subtraction here, which we can just start here, subtract this, add this, and subtract that. All right, so I'm going to start with 0.57598 minus 0.031847 plus 0.000528 minus 41773 equals. All right, the answer came out to 0.544658. That is the sine of 33 degrees, and that's given to us in radians. Okay, now here's the cool thing. That, what I'm claiming is that right there is this distance. On a unit circle of radius 1, this number that we just calculated without using any trigonometry, we used the Taylor series, which I know you're probably thinking this is a lot more complicated than using trigonometry, but I assure you it isn't. The beauty is you don't need a trigonometry function calculator. You don't need it. You just need to think about trigonometry and think about your unit circle and express what you're looking for in terms of a sine, and then use this Taylor series approximation, and you can come up with it. We just proved that you can do this without having, you know, how do you do trigonometry with a dollar in your pocket? Well, I think I got this at the dollar store for like $1 or $2, okay? Pocket change. All we need is a compass. That was 12 bucks. A precision compass. You could probably get away with using one that costs $1, to be honest with you. So for less than a cost to buy a couple of lattes at Starbucks, you can do trigonometry. All right, but we're not done yet, okay? So I'm claiming that with the information we have, we can find this distance right here. Now let's keep in mind where we are. So 0.544658. Back to our cool circle here. Let's see if I can show all this on one screen. Yeah. So this triangle right here is the same as this triangle right here. It's just been flipped. So all I did was turn the thing around. I twisted it all around. It's the same triangle. It's just flipped around. Well, I'm claiming now that this distance right here, right there, is this number, 0.544658 radians. That's what I'm claiming. So I'm also claiming that now that we know this side, and we know this side, this is 1, the radius, we can find this. Not using trigonometry, this time we're going to be using the Pythagorean Theorem. So, if this is a radius of 1, and this inscribes an arc, this is also a radius of 1, just like on the other circle. I'm not going to refer to this as the hypotenuse. I'm going to refer to this as the radius of unit circle 1, and I'm going to call that 1. So if this distance right here is equal to 0.544658 radians. Now, keep in mind, I'm going to actually make this very clear. So what I'm pointing out on this distance here is not the radian for the arc. I'm pointing out this is equal to the sine of 33 degrees. This arc radian measurement, let's make sure we've got this clear. This one was 0.57598 radians. So this is 0.5446568 radians. That's equal to sine of 33. So this distance right here is what we're going to find from finger to finger right here. Now that is equal to, we know that that's equal to the cosine of 33. That's the cosine of 33. That's that length. Because now we're thinking of this as the distance to the wall, right? But if I remember my identities, go back to this here. This distance, the same distance. This distance is the sine of 57. So we just have to think about triangles for a minute to see that. Let's look at it this way. Let's say the wall's over here. The sine of 57 is this height. Well, the sine of 57 is also the cosine of 33. But we don't need to do any more Taylor series approximations. We don't need to do that. We can combine our knowledge of geometry with our knowledge of algebra, because that's all this is, guys. That's algebra. It's barely even algebra. It's really just plugging numbers into a formula. The Pythagorean Theorem will give us everything we need. Now, let's make some space. The Pythagorean Theorem is a squared plus b squared equals c squared. Well, I don't know a, but now I know b. So let's call this a, and we'll call this b, and we'll call this c. I don't know this. This is what I want to know. But I know these other two, so I can find it. So I know what b is. B is 0.5446568 radians. So if I say a squared, which I don't know, plus 0.5446568 radians squared equals c squared, which is 1 squared. Well, 1 squared is 1. So this is going to be easy. So now let's isolate the term we can't find. A squared equals 1 squared is 1. Is that fair enough? 1 minus 0.5446568 radians squared. So all I need to do is square this to come up with and then subtract it from 1 to come up with a squared. Okay, so I just need to square this. Let's take these numbers exactly as they appear. 0.5446568 times 0.5446568. And that gives me 0.29665. So that's equal to 1 minus 0.29665 6, 5, 1. We'll just leave it there. That's a squared. So now let's actually subtract that from 1. And you get 0.7033, and then I'll round up 9. That's a squared. So in order to find a, we need to take the square root of this number. Take the square root of that number. Now I don't have, oh I do have the square root. I didn't realize that. This calculator has a square root on it. So I can take the square root of this number. 0.703349 square root gives me 0.8386590. So a equals 0.8386590. That's a. So that is the distance from here to here. The cosine of 33, okay, equals, let me just write this out, equals the cosine of 33 degrees, which equals the sine of 57 degrees. So this is in fact what we were looking for the whole time. We're not yet to our problem, but we've actually created the base ratio, or the base decimal, that we're going to multiply by our scale factor to scale up from a circle of radius 1 to a circle which has that distance in it, that cosine distance of 48 meters. Okay? So, let me transfer back to my drawing that what we know now. So we know that this distance right here if I make some space, the sine of 57 degrees equals, I'm going to refer back to this just to write it down, equals 0.838659 radians. Okay, and we'll just write that, just so we remind ourselves, that also equals the sine of 33 degrees. I apologize, mistake. The sine of 57 degrees. I need to correct that. So sine of 57 degrees equals 838,659 radians, and that is equal to the cosine of 33. I just need to correct that. Okay, now we need to kind of scale up to our scale factor. I guess we can also write in this distance here, because this is the cosine. Tell them everything we know. The cosine of 57 degrees equals 0.5. So I'm referring back to this side here. 0.54658 radians Okay, so cosine of 57 degrees equals this, 0.5446568 radians, which is equal to the sine of 33 degrees. So the mistake I'd made before, this was supposed to say cosine. I'll just let that absorb in. So now we have to figure out how to solve our problem. Let's just look at this for a minute. In our original problem, it said we're standing 48 feet away from a wall. Or I keep saying feet. 48 meters away from a wall. We don't know how high the wall is, but we know that we're standing 48 meters away from it and that we're making an angle to the wall of 57. We want to know what that height is right there. So we don't know that. And remember, we're working with a unit circle of radius 1 here. 1. And now we're scaling up. We're scaling up. We don't know the scale factor yet, but that's okay. We can find it very easily. So let me show you a couple things here. We know our numbers now. We know this distance will be some ratio to our 48. So I can find the scale factor very easily by taking 48 meters and saying basically that, let's put it over here, equals 48 meters equals the, because I can call this here, this distance, I can call it the cosine of 57, or I can call it the sine of 33. Now you see, this is either the cosine of 57 or the sine of 33. Doesn't matter what I write, but both of those numbers, the cosine of 57 or the sine of 33, refers to this radian measurement. So I'll say 48 meters equals x, which is my scale factor, times 0.544 6, 5, 6, 8 radians. So in order to find x, I just divide by that radian measurement for the cosine of 57 or the sine of 33. So I'll just divide by 0.544658, and that will equal x. So let's do that. .48 divided by 0.544658. All right, that gives me my scale factor of 88.12889. All right. So x equaled 88.12889. That's our scale factor. So I'll actually write that in. This is what we'll call the scale factor. So if this distance for a unit circle of radius 1, this distance right here was equal to 0.5446568 radians. If I multiply that by 88.12889, let's just do it, okay? Take that right there. This is my scale factor, and I multiply by the radians, I'm going to get 48 meters. 0.5446568. See the approximation accuracy? What did I tell you? I said it was that when we do this without the trig calculator, this should amaze you, ladies and gentlemen, because we come within, I don't even know, 1/10,000,000th of the correct number, which was 48 meters. So the approximation is to a 10,000,000th decimal point accurate, because I round up to 48. That should shock you, and it's amazing. We did all this trigonometry with just a 4-function calculator. But wait, you say, we already knew that it was 48. So what? Well, how do I calculate the height? That's what I wanted. Well, no problem. We know that factor as well. The sine, or height, the sine of 57, or the cosine of 33 is this distance right here. Well, we know that distance for a unit circle of radius 1. It's 0.838659. Well, all you have to do is multiply that times the scale factor in order to find out what the height is. So we'll do that now. So if I want to know the sine of 57 degrees for this circle, the sine of 57 degrees for a circle whose cosine of 57 degrees equals 48 meters. Think about it like that, because that's what we know. We know 48 meters. The sine of 57 for a circle whose cosine of 57 degrees is 48 meters. What I do is I take my sine of 57 radian measurement for a unit circle of radius 1, and I multiply by my scale factor. So I take 0.838659, and I multiply by my scale factor of 88.12889. Because I'm scaling, you think about it, I'm scaling up from the unit circle to the circle where the cosine distance isn't 0.5446568 radians, but it's 48 meters. And that scale factor was 88. That's kind of like the conversion between radians in a unit circle of radius 1 and a real world situation where I'm standing 48 meters away from a wall. Okay? So let's see what that comes to. This is the moment where we achieve our goal. So I'm going to do this right here. 0.838659 multiplied by our scale factor. I want you to see it happen. Of 88.12889. Ready? This is going to be the height. If you're standing 48 meters away from a wall at an angle of 57 degrees, this is the height. 73.91 meters. 73.91 meters. So now we know this distance is 48 meters. That was given to us. And now we know this distance is 73.91 meters. So now we need to find the hypotenuse. That's what I said. I don't want to use that word. I want to use the radius. Okay? Well, I can use the equation of the Pythagorean Theorem. Okay, and I'm going to do that. But let me see. I want to see if there was another way to do it. If I take 0.99487 times 88. Okay, so here's what I want to test. I want to test a theory in real time. Now, we have our radian measurement for the... Oh no, I don't think that would be right. We have our radian measurement, and we could scale it up. I don't think so. I don't think that's going to do it. I don't think that's going to do it, is it? The radius. The radius is 2 pi r. I don't feel comfortable with that. We'll use, I think there's probably something there, but we'll use the Pythagorean theorem. There probably is something there, and I want to think about that. How could we use the radian number and just multiply by this factor to get the quote hypotenuse, air quotes, or radius. I know there's a way, but I just don't want to mess with it. Let's use the Pythagorean theorem. So this is A, this is A, this is B, and this is C. And now we know A is 73.91 meters, or pardon me, A is 48 meters, B is 73.91 meters, and we don't know C. Let's see what happens. So A squared plus B squared equals C squared. Well, A squared, that's 48 meters squared plus B squared, the height, or sine of 57, is 73.91 meters, and that's going to be squared as well, equals C squared, which we don't know. So let's take 48 times 48, and that equals 2,304. 2,304 plus 73.91 times 73.91 equals 5,462.6881. All right, 5,462.688 equals C squared. So C would be the square root of this sum. So I'll just add back this number here, 2304, and then I'll take the square root of that number. That gives me 88.1288. 88.1288 equals C. Now here's the miraculous thing. Where have we seen that before? Right here. That's what I was hoping would happen. Because the unit circle has a radius of 1, and once you throw out the word hypotenuse and you only call it radius, it makes sense, doesn't it? Because the unit circle has a radius of 1 and the scale factor was 88.12889, so it's 88.12889 times as large of a circle as the one that's right here. Well, if the hypotenuse, if that radius is 1, 88.12889 times that radius should give us the radius for the fully scaled model where this distance isn't 0.544656 radians, but it's 48 meters. So if this is 48 meters and this is 73.91 meters, this is 88.1288 meters. Okay, there it is, 88.1288. So what I'll add in here, just so this is all clear, is I'll call this A, and I'll call this B, and I'll call this C. And then I will write in, in a nice consolidated area what our answers are. A, B, and C. So A was 48 meters. B was 73.91 meters. And C, the radius, was 88.1288 meters. Which happened to be equal to our scale factor. And this, ladies and gentlemen, is a tutorial that I think everyone should watch, because you are taught to memorize trigonometric functions without knowing what you're computing. Notice at no time today did I use the word tangent. I mean, I did probably use the word, but we didn't use tangent. It turns out you don't need to use tangent to compute this. Now we can find tangent because tangent is just the sine over the cosine. Now I'm wondering if we shouldn't just find it for fun. Maybe we should find it. Let's just find it before we leave this so you can check everything. But here we'll call this the answers. All right, for fun, just because we're bored, let's remind ourselves that the tangent of 57 degrees is equal to the sine of 57 degrees divided by the cosine of 57 degrees. Okay? Well, let's use our radian measurements to figure this out. We know that this is 0.838659 radians divided by 0.5446568 radians. And this will give me the tangent of unit circle 1. That's tangent of unit circle 1. That will be the length of the thing called tangent, which I will show visually, maybe on this diagram. Maybe I will. I don't know. We'll see. Maybe in another video all its own, but let's just compute it for now. If I take 0.838659 and divide by 0.5446568, that gives me 1.53979 radians. For unit circle radius 1, this is the tangent. So, for circle radius 88.1288, what is the tangent? Well, so what we do is we just take this and multiply by 88.12889. That's our scale factor. And we'll get the tangent at, so we're actually doing something slightly different here, so I want to make sure we know that we're doing something a little bit different. We're doing this. We'll multiply this times 88.12889 0.12889, and that equals 135.7 meters. So in our example, this is the tangent. If we wanted to find that in the example. I will show in a future video that the tangent, I suppose I could show it now because we're doing it. Let's show it now what it is, just so you know what it is. All right, let me show you what the tangent is. First, we need to extend this line out a little bit. All right, and we need to extend this line out a little bit. Okay, now what the tangent is, think about a circle, just any old circle. The tangent is a line that comes along and touches the circle at just one point. So there's a tangent right there. The tangent of that little point right there would be like bringing in a line that hits it just at that one point. That's the tangent in geometry, if you remember that. And the way we find a tangent with an actual radius drawn in is we want to find the point that is exactly 90 degrees or perpendicular to that radius. So if I wanted to find the tangent of 57 degrees, for example, I need my little cheater tool, because it's not one of those special angles. I come in here, get everything straight, and set this guy right at 90, and then make a couple of little marks carefully. And then I can draw in my tangent line. I just made a few guide marks. And I'm going to bring that, you can't see what I'm doing, I'm going to bring that line all the way down until it hits the line that I drew. Okay? So now, in order to complete this tangent system, I need to draw a vertical line going up out of this triangle or circle. So I find points that pass, I can use the sacred geometry of the flower petals to find points that pass through all those flower petals. See? I'm going to make a perfectly vertical line. Just like that. Okay. So here's the cool thing here. This distance right there is the tangent. And that is equal to, for a unit circle of radius 1, it's equal to 1.5, for a unit circle of radius 1, tangent of 57 degrees equals 1.53979 radians. Okay, that's this distance right here. The remaining distance, if we draw a line from here to here, that distance from right there to right there, that's the cotangent. That's just 1 over the tangent. So if I wanted to find the cotangent, I could just take 1 divided by, depending on, let's do cotangent of the big numbers, the scaled up numbers. 1 divided by 135.7. Oops. I guess I'm going to need to do this starting with this radian figure here. So let's take 1 divided by 1.53979, and that gives me this number right here. All right, that's the cotangent here. That's right. Cotangent of 57 degrees equals 1 over the tangent of 57 degrees, which equals 0.649432 radians. That's this distance right here. This whole distance right here in radians was 1.53979. This distance right here is 0.64392 radians. Now, if we scale up, go back, scale by 88.12889, we get this times 88.12889 equals 57.2343 meters. 57.2343 meters. I'll show you something cool. This distance from here to here, that distance right there, that is the secant of the line. If you've always wondered what is secant and cosecant, that's what it is. So we can draw it in if you want. That's the secant. So this whole distance right here is the cosecant, like the vertical portion of the secant. This distance right here is the secant. And it's composed of several parts. This right here is the cosine. This little part right here is called the versine, V-E-R-S-I-N-E. And this part right here is called the x secant. This distance from the edge of this circle to this point, x secant, versine, cosine. So here's something cool. This distance right here, this line, is the versine, because you kind of take your fingers and just go zoop. You see that it, pardon me, I said versine, x secant. This is the x secant. If I go zoop, then I've got that same distance, I've maintained it. So x secant rotates all the way around. So this is also the x secant. Just do it visually. It's all the way down, it's the x secant. So that's the whole line there is the secant. The secant is equal to 1 over the cosine. That's what it says. Well, we can do this. Okay? So we can actually find this length, 1 over the cosine. So let's just say over here, secant equals 1 over the cosine. Well, for a unit circle of radius 1, the cosine of 57 degrees, so we'll say 1 divided by, we'll go down here and find our 0.544658868, whatever. 1 divided by the cosine of 57 degrees, and for a unit circle of radius 1, is 1 divided by 0.5446568 radians. So let's get that. This will be the radian measurement of the secant of 57 degrees. So I'll say secant 57 degrees. One divided by 1 divided by 0.5446568 gives me 1.8360 radians. So for a unit circle of radius length 1, the distance from my finger here to this point right here is 1.8360 radians. And all we really needed to find that was we needed to make a right angle right there, find our tangent line, extend out this line, and where that hit, we took the compass and we made a new circle like that. Okay? So let's scale this up and find out how long the secant line would be in our scale up factor. Scale up by 88.12889. Okay, we're scaling up. So I'm going to take that secant and I'm going to scale up by 88.12889. And that gives me a secant length equals 161.8 meters. That's the secant length. Would be there. Okay, the secant length. The secant length is 161.8 meters. So now we found the tangent, the cotangent, the secant. We could just keep finding trigonometric numbers using this simple system that we've come up with. But this video alone is now an hour and a half. I think that's long enough. I hope that this series of videos has been helpful and that you now have a more intuitive and comprehensive understanding of just how to compute things visually using the unit circle. All right. I will show for you, if you want to see a diagram that shows all of the trig functions on the unit circle. I think you're now sort of ready to see this in the Zen sense of the word. There it is. So that's what we created on in our example. That's what we created. If you look at it, I'll show them side by side so you can see that that's what we did. See how that's what we did? We did the same thing. I'll put it over on the left side to show you that that's exactly what we did. You can just look at that for a while. And this image that I'm showing you in the box, this is for an angle of 45 degrees. So that's why those lines aren't parallel. So this example right here that's in your window frame right now is for an angle of 45 degrees. But that shows all of the trig functions. So screenshot that. I'll make it big again. Screenshot that if you want. That shows all of the different trig ratios or trig functions on it visually. And with that, I will thank you for your time and your attention. Sacred geometry is amazing stuff. I hope this helps you learn how to do trig without spending money on a TI calculator. Thank you again.